In this lesson, we are going to learn about the structure of an atom. Now, we know that atoms are the basic building block of all matters in this universe. But there are tiny particles called subatomic particles. Think of the prefix sub, so something that even smaller than an atom. In this case, these subatomic particles make up atoms. And there are three types: proton subatomic particles, then we have the subatomic particles of neutron, and lastly, we have the subatomic particles of electrons. Now, right here, we have the nucleus of an atom, and around the nucleus, we have orbits. Well, of course, atom can be presented in terms of electron cloud as well, but it is easy to understand the structure of an atom looking at the Bohr model. First of all, let's try to find the location of the subatomic particles. If I were to place the subatomic particle proton, notice how the proton go directly to the nucleus because that's the location of all proton. And I also try to place the neutron. Notice how I try to place on the orbit, it doesn't work. And there you go. The neutron also go into the nucleus. Notice how here we have the symbol for it. This right here represents the mass number. Over here represent the atomic number, also the number of proton. Then right here it represents the charges. Notice how when I take away the proton, the charge becomes 0. That is because each proton has a charge of +1. And what about the neutron? If I take away the neutron, it doesn't affect the charge, but it affects the mass. And the mass of the neutron is equal to the mass of the proton by 1 AMU. So notice how we have two subatomic particles in the nucleus. Proton has a mass of 1, neutron has a mass of 1. And the unit is called AMU, atomic mass unit. And then I add in another proton. Look what happened to the element. It moved to the next element, and now we have the element helium. And look what happened when I add another proton. It becomes another element. So the number of the element equal to the atomic number, which also represent a specific element on the periodic table. Let's try adding another element. It becomes another element. And if I remove it, it now go back and become the previous element. So in the end, you can see that the arrangement of element on the periodic table is based on an increasing number of proton. When I add in one more proton, it becomes the next element. And I add another proton, it becomes the next element. And when I add in the neutron, it doesn't change the element at all. So that tells you that an atoms of an element can be different. Because look, if I add another neutron, it's still the same element, but it's completely different atoms. So I adding another neutron, look how it's still boron, but the number of neutrons change, and the mass number in the end also change as well. So adding another neutron, look how the mass number changed. If I remove the neutron, the mass number also changed. But in the end, it is still the same element. So the number of proton, which is also equal to the atomic number, determine the element, where the number of neutrons just change the mass of that atoms. So again, the same element can have different atoms because the number of neutrons can be changed. And let's look at the number of electrons. What happened when I add an electron? Notice how it was +5 and become a +4. So that tells you that the electron has a negative charge. Let's add in another negative charge. And look what happened. It's become +3. So we have +5, that's coming from the proton, and -2 from electron give us a net of +3. Let's adding 3 more electrons. See how it's decreased by 1 because canceling out with a positive proton. And then we add another one. But keep that in mind, why doesn't this go in here anymore? See how it bounced away? That is because the first orbit or the first energy level can only hold the maximum of 2. And that's the reason why you can only put 2 electrons here. And then if we want to add more, is always go out to the next ring or the next orbit. And look what happened. We have 5 electrons that cancel out with a 5 positive proton and give us a net charge of 0. And then lastly, we have electron cloud. Look at this. Notice how electron cloud, we don't see the boundary or the orbits of the first energy level or the second energy level. That's why the Bohr model or the model that use orbits usually represent the structure of an atom. It allows us to see the different energy level of electron. And let's go back again. We're adding another proton. And look at that, it go into the center, which is the nucleus. The only thing that's wrong about this model is that the nucleus is too big. The nucleus is extremely small, very, very small, to the point that you cannot even see it. Okay, so now let's compare it to something that we know in terms of the size of an atom. If the nucleus is about the size of a blueberry, the entire atom will have the size of a football stadium. So that tells you how small a nucleus is. And that tells you that the majority of the atoms is mostly empty space. And the majority of the mass, in this case, we can see that when we add in proton, it is in the nucleus. And when we add in the electron, it doesn't affect the mass at all. So therefore, the mass of an atom is the sum of proton and neutron. So the mass of an atom is concentrated in the proton and the neutron located in the nucleus. And because the nucleus is extremely small and contains the overall mass of an atom, that tells you that the nucleus is extremely tiny, but it's also extremely dense. Now let's look at the different notation that we can use to represent a specific atom. First of all, we know that this is the Bohr model, and this is the nucleus with a boundary that separates the nucleus from the level of electron. But in reality, there are no boundary. And we use the Bohr model, this is the Bohr model, to show electron travel in circular orbit. So we have the first energy level and the second energy level, or the first orbit and the second orbit. Then we have a new term being introduced to us called the valence electron. And the valence electron are the electron in the outermost orbit. So this would be the inner. And of course, this one would be the outermost. Here's the most common notation of atoms that we use. First of all, we have a number on top, and this number on top is always larger than the number on the bottom. That is because this number represents the mass number. And the mass of an atom, we remember that is equal to the proton plus the neutron inside the nucleus. The number of electron doesn't have any mass. It's extremely tiny and is extremely light. So that's the mass number, top larger than bottom. And what does this bottom number represent? That bottom number represent, we learned that is equal to the atomic number, which also equal to the number of proton. And we know that the number of proton is how the elements are arranged on the periodic table. So that means if we know the number of proton, we also know the name or the symbol of the element using our periodic table. For example, if I look at element of carbon, we know that carbon has the atomic number of 6, and therefore it has 6 number of proton, which represented by the symbol C for carbon. And the last number is right here. We have the charge. Notice how the minus follow the number. This represents the charge of an atom. In this case, this charge is equal to proton minus electron, because a proton is the positive and the electron is negative. They cancel each other out. When you have more electron, which means you're going to have a negative sign. And when you have more proton, you're going to have a positive charge. So in this case, you have -2. That tells you have 2 electrons extra. Another form of notation is this one right here. We have the element, or usually represented by the element symbol, and then we have the mass number. And if we look at this format closely, we know that if we know the element symbol or the element name, we also know the number of proton. And then if we know the mass number again, we also know the number of neutron, because the element symbol will give us the number of proton, and this is the mass number. So we can solve for the number of neutron easily. Basically take the mass number minus the number of proton, and that gave us the number of neutron. So in this task, we are going to look for the name of the element, the number of proton, the number of electrons, and the number of neutrons. So I have this notation that represents these atoms of aluminum. So in this case, we know that this represents the mass number, which is 27. So that would be the mass number right there. And then that would represent the number of proton. And this represents the charge. So let's go back. Do I know the element? Of course. This element, Al, is aluminum. So that's the element aluminum. And then what about the number of proton? Is number 13. Okay, because that number right there represents the atomic number as well as the number of proton. And the mass number is 27. So again, we go back and solve for the number of neutron. So neutron is basically mass number minus the number of proton. So neutrons equal to 27 minus 13, and that will give us 14 neutrons. Isn't that easy? And then what about the number of electrons? So the number of electrons, let's go back to this equation here. To solve for the number of electrons, there are two ways that we can solve for it. First of all, we can set this up as an equation. Of course, the number of electrons is equal to the number of protons minus the charge. So in this case, we have the number of protons equal to 13 minus the charge. What's the charge? In this case, the charge is 3 plus, so that'll tell you there's 3. So what's 13 minus 3? That gives us 10. And here's another way to do this. Notice how we know that the charge is equal to proton minus electron. So when we have a negative, that means we have extra electron. And when we have positive, that means we lost electron. But what happens when the charge is 0? When the charge is equal to 0, that tells you that the number of protons is equal to the number of electrons. And that's the only way that it cancels out equal to 0. So in this case, we have a plus 3. That means we have 3 less electrons. We don't lose proton because proton is all the way inside the nucleus. So we have 3 less electrons. What does that mean? Here we have 13. What's 3 less? Of course, it is also 10 electrons. So that's another way of doing it. By looking at the number of protons and look at the charges. When it's positive, we have lost a certain number of protons. In this case, positive 3. That means this atom has lost 3 electrons. When it's negative, it has gained extra electrons. And this is possible because atoms can easily lose or gain electrons to be stable. And we talk more about that later. Now let's try another example. Here I have this atom of oxygen. First of all, we know that this is the mass number, okay? And this is the number of protons. And we know that the number of protons in this case is 8. And what about the number of neutrons? Go back again, neutron is equal to mass minus proton. So we have neutron equal to 16 minus 8, give you 8 neutrons. And then the electrons where it gets tricky. When this atom has a charge of 0, the number of protons is equal to the number of electrons. But now we have the charge of negative. Negative electrons are negative. That means it has 2 extra. What's 2 plus 8? That gives you the number of electrons equal to 10. Or we can use the mathematical way, proton minus the charge, which in this case, the proton is 8 minus the charge. In this case, the charge is negative. 8 minus negative 2 give us 10. And the same way we get our 10 electrons. But this is a lot easier to understand because, again, when the charge is 0, the number of proton equal to the number of electron. But in this case, the charge is negative, and that tells you it has 2 extra electrons. So 2 extra electrons plus 8, that gives us 10. So that's pretty easy. Now let's try this one. We have this atoms of helium right here. Notice the charge, there's nothing there. So we know that is 0. So this is our mass number. This is our number of protons. So therefore, we know the number of neutrons equal to mass. Again, mass number minus the number of proton. In this case, it's equal to 4 minus 2 give us 2 neutrons. What about the electron? Remember, this is 0. And when that is 0, the atom is neutral. If we look at proton minus electron, the only way that's equal to 0 is that the number of proton is equal to the number of electron. So therefore, the number of electron must equal to the number of proton, which is 2 electrons. Here I have carbon. Okay, so for carbon, there's no charge here again, but the mass number is 13, and this represents the atomic number, which is equal to the number of proton as well. And then therefore, in this case, that represents the number of proton. And what about the neutron? Neutron, again, is mass number minus the number of proton. So 13 minus 6 gives us 7 neutrons. And here's the tricky part, finding the number of electrons. Notice how we don't have a charge here. We assume that's going to be a 0. When the charge is equal to 0, the only way that's possible is when we have a plus equal to the number of negative. In this case, there are 6 plus. The negative must be 6 as well, and therefore tell you that the number of electrons must be equal to 6 as well. Let's try another one in a different form of notation. We have carbon 12. And we look at the format, this is the element and this is the mass number. So this is carbon. And what's so important about carbon? We use the periodic table, look for carbon, which is represented by C. So that tells you right there, that's the atomic number, okay? So that's also equal to the number of proton. So that tells you the number of proton is equal to 6. And what about the neutron? The neutron is mass number minus proton. So the number of neutrons is equal to 12 minus 6, give us 6 neutrons. And then we have the last one, which is electron. It's very tricky. Notice how in this notation we don't have the charge of the specific atoms of carbon. That tells you we can assume that the charge is equal to 0. So if the charge is equal to 0, we know right away the only way that's possible is the number of electrons must equal to the number of protons. So therefore, the number of electrons must be equal to 6 as well. We have boron. And what is boron? Boron is, in this case, if we go back to the periodic table, boron's right here, is represented by the atomic number 5, which equal to the number of proton as well. So that tells you that there are 5 protons. And this, again, is the mass number. And from there, we can find the number of neutrons, which in this case is equal to mass number minus proton. So 12 minus 5 can give us 7 neutrons. And then what about the number of electrons? And the number of electrons, again, we don't have a charge, so we assume that it's going to be a 0. So the only way that's possible for the charge to be 0 is that the proton equal to the number of electrons. So therefore, your number of electrons must equal to 5 as well. Now, lastly, we have this format right here for sodium. Notice how we have positive. What does that positive represent? It must be a positive 1. The same thing when we have negative, we have to assume that is a negative 1, even though the 1 is not written there. In chemistry, usually the 1 is often not written. So when you see positive or negative, you assume that it's 1 relatively. Okay? So in this case, we know this is the mass number. This is the number of proton, or the atomic number. And in this case, the sodium represented by, look at that, atomic number 11. See how an element is represented by a specific number of proton, or atomic number. Now, let's find the number of neutron. We know that mass number minus proton give us neutron. So we have 23 minus 11 give us 12. So we have 12 neutrons. And the number of electron is where it gets tricky. Again, let's go back to use our logic. When is a charge of 0, the number of proton equal to the number of electron? In this case, it's a positive 1. That means it has 1 less electron. So if 11 have 1 less electron, the number of electron must equal to what? 10, of course. Or we can use this mathematically. We take the number of electron equal to proton minus the charge. So we look at it that way. The number of proton is 11 minus the charge, which is positive, so minus 1, and give us 10. So either way, we will solve for the number of electrons. And that's all we have to do.